Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss new chapter, coordination compounds. Coordination compounds are the backbone of modern inorganic and bioinorganic chemistry and chemical industry. In the previous chapter, we have learned that the transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anion or neutral molecules. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structures have provided insight into the functioning of vital compounds of biological system, as for example chlorophyll, hemoglobin and vitamin B12. These are coordination compounds of magnesium, iron and cobalt. Again I am telling you, chlorophyll, hemoglobin and vitamin B12 are coordination compounds of magnesium, iron and cobalt respectively. A variety of metallurgical processes, industrial catalysts and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplating, textile dyeing and medicinal chemistry. Now I am going to discuss Werner's theory of coordination compound. Werner's theory of coordination compounds. Alfred Werner, a Swiss chemist, was the first to formulate his idea about the structure of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of a primary valence and a secondary valence for a metal ion. Binary compounds such as CrCl3, chromium trichloride, cobalt chloride CoCl2 or PdCl2 have primary valence of 3, 2 and 2 respectively. Binary compounds such as CrCl3, cobalt chloride, CoCl2, PdCl2 have primary valence of 3. In CrCl3, chromium has 3 valency. Cobalt has 2 valency. Palladium chloride, Pd has 2 valency. In a series of compounds of cobalt third chloride with ammonia, it was found that some of the chloride's ions could be precipitated as AgCl on adding excess silver nitrate solution in cold. This important point I am telling you. In a series of compounds of cobalt third chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate solution in cold, but some remained in solution. Some precipitated and some remained in solution. Example I am telling you, 1 mole cobalt chloride 6NH3, it is actually of yellow color. 1 mole cobalt chloride CuCl3 6NH3 cobalt chloride, it gave 3 mole AgCl, 3 mole AgCl. And 1 mole cobalt chloride 5NH3, it is of purple color, gave 2 mole silver chloride. And 1 mole cobalt chloride 4NH3, actually NH3 is differing. In the beginning, cobalt chloride 6NH3, its color was yellow. Color is also changing along with the number of ammonia. Cobalt chloride 6NH3, its color is yellow, and if excess AgCl was added, then some AgCl precipitated out, means 3 mole AgCl precipitated out. And in second case, cobalt chloride 5NH3, in this case 2 mole AgCl precipitated out. And in third case, cobalt chloride 4NH3, its color is green. 1 mole AgCl precipitated out. And again 1 mole cobalt chloride 4NH3, its color is violet. Now you will tell this cobalt chloride 4NH3, its color is green, and it gave 1 mole of AgCl precipitated. And cobalt chloride 4NH3, its color is violet. Both have same molecular structure. CuCl3, 4NH3, its color is green. Same molecule, 1 mole, same molecule, cobalt chloride 4NH3, its color is violet. Okay, both are same molecule. Structure formula is same, but color is different. One is green, other is violet. And in this also, on addition of silver nitrate, it gave 1 mole AgCl. Then see here that in the beginning 3 mole AgCl precipitated. In second case 2 mole AgCl precipitated. And last two 1 mole AgCl precipitated. Why did it happen? This is the question mark. Werner observed all these things. These observations, together with the result of conductivity measurements in solution, can be explained if, first I am talking about if 6 groups in all, either chloride ions or ammonia molecules or both, remain bonded to the cobalt ion during the reaction. Okay, and in second case, the compounds are formulated where the atoms within the, actually it is written in the bracket, a square bracket. Means how will you represent coordination compound? I will tell you. But here this observation observation that why they have given 3 mole, in other case 2 mole, in other cases 1 mole. Why? Then in that, because silver nitrate you have added, correct? Then here silver nitrate, when it was added, then in one case they have given 3 mole precipitate of silver chloride, in other case 2 mole silver chloride, and other 2 cases 1 mole. And then why? Then these observations together with the results of conductivity measurements in solution can be explained if 6 group in all, either chloride ions or ammonia molecules, including both, it should be 6. Including chloride or ammonia molecules, it should be 6. Okay, total should be 6. Remain bonded to the cobalt ion during the reaction. Silver nitrate you have added. Then in the first case COCl3 was there, COCl3 6NH3. You have added excess silver nitrate. Then what happened? That now 3 chloride precipitated out of 3 cobalt chloride was there. That 3 mole AgCl it has given. In other 2 mole they have given. 2 mole AgCl given. 1 mole was attached with cobalt only, and 5 NH3. Then in the beginning only 6 NH3 was attached to the cobalt, and 3 Cl3 was there. That 3 Cl converted to AgCl. But in the second case 5 NH3, because total 6 can be accommodated. Then now Cl3 and 5 NH3, total 8 was there, but there should be only 6 maximum. Then 2 Cl precipitated as AgCl. And next cases 7 was there, cobalt 3, COCl3 4 NH3, total 7 ligands were there, 4 NH3 plus 3 Cl, total 7. Then here maximum 6 ligand can be attached to the cobalt. Okay, then that's why now 4 plus 2 remained and 1 precipitated as AgCl. In last case also same case, 1 mole AgCl precipitated, because total 6 remain bonded to the cobalt ion during the reaction. Okay, it means total 6 ligand was attached to the cobalt. Now here what is the important things, that compounds are, I will tell you example how compounds are, formula of the compound, how will you write, I will tell you. Okay, the compounds are formulated where the atoms within the square brackets form a single entity which does not dissociate under the reaction condition. Okay, atoms within the square brackets form a single entity which does not dissociate under the reaction condition. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. This is the important thing. Werner, scientist, chemist, Werner proposed the term secondary valence for the number of groups bounded directly to the metal ion. In each of these examples, the secondary valence are 6. That's why always 6 molecules, that is called ligands, which is molecules which is attached to the metal is called ligands. Then 6 ligands attached to the, always in every situation, total 6 molecules attached to the cobalt. In first case you have seen that 5NH3 1 Cl, other 4NH3 2 Cl, and in third 4NH, again fourth also same. Then here actually you should understand that complex ion means CO cobalt, with cobalt ammonia, 6 ammonia is attached. Then this is actually called complex ion. It is written in bracket, square bracket, and charge is written outside. Then there are two type of valency or balance: primary valency, secondary valency. Then primary valency is common, just like NaCl, sodium chloride, only one valency. Okay, calcium sulfate, CaSO4, calcium sulfate, here sulfate is 2 negative and calcium is 2 positive. Okay, then there is also primary valency is 2. Calcium has 2 primary valency. Like that way, AlCl3, aluminum trichloride, AlCl3, Al has a 3 plus, and Cl3, 3 Cl is attached. Then here, these are the common primary valency, only 2 type of cation and anion is there, ordinary cation and anions. Okay, but here in a complex compound, actually Na2SO4 also, SO4 2 minus is there, then 2 Na is there, Na plus. Then here this sodium has this thing primary valency 1, then 2 primary valency plus 2, that neutralized 2 negative of sulfate. Then these are actually these things examples of primary valence: copper sulfate, Cu2 plus, Cu2 plus and plus SO4 minus. Copper has 2 plus and sulfate has 2 minus. Then these are the examples of primary valency or primary valence. But now you can see in this case coordination compound, this complex, in coordination compound, that complex ion is written in the square bracket, as for example cobalt NH3 whole 6, that is written inside the bracket, square bracket, and outside 3 plus. Cobalt has 3 plus primary valency, 3, cobalt 3, correct? Always remember cobalt has 3 valency. And here ammonia is a neutral ligand. Actually this ammonia directly it will just attach to the empty d orbitals of the cobalt metal. Okay, d orbitals. It is cobalt is a transition element, you know. Then it has vacant d orbitals. 6 vacant d orbitals it has. Hence this 6 ammonia lone pair, they all have ammonia have lone pair of electron. One pair of electron they have, means 2 electron ammonia have. Each 6 ammonia have 2 electron each ammonia. Then this 6 ammonia, they will donate these 2 electron to the d or vacant d orbitals. 6 vacant d orbitals were there. Then these ammonia having lone pair of electron 2. Okay, 2 electron. Each ammonia on a nitrogen they have 2 electron. That is called lone pair of electron. That will give to the 6 d orbitals and they will make coordinate bond. Okay, coordinate bond. Then maximum 6 this was there, orbital was there, hence only 6 bond it can make. Then here all 6 has been given by, all 6 bond is made by ammonia only. One pair electron each ammonia has given. On nitrogen 2 electrons are there, that is called one pair. Then 6 ammonia has given. Total 12 electron. Every orbitals 2 electron given, means one pair, 6 pair. That's why these are making 6 coordinate bond directly to the d orbitals. Then this is actually, this bond forms the complex compound. Then CO will be in the middle and 6 hydrogen, it will make bond with cobalt. Okay, 6 bond surrounding the cobalt. 6 ammonia will attach, they will make coordinate bond. Then this is actually complex molecules. It is called complex molecules because each ammonia has no charge, all are neutral. Ammonia has no positive, no negative charge, only lone pair. Then this is the neutral. Then but cobalt has 3 valency. Oxidation state is 3. Hence in a square bracket, complex ion is written cobalt NH3 whole 6 in a square bracket. Okay, and outside 3 plus, because cobalt has 3 oxidation state. Then to neutralize this 3 oxidation state, 3 plus charge is there, hence to neutralize this 3 positive charge, any 3 negative molecule can come, or ion you can tell, because it is a positive, then it will be neutralized by negative ion. As for example, 3 positive charge can be neutralized by 3 negative chloride, or 3 negative bromide, or 3 negative iodide. Like that, any negative charge can neutralize this positive charge. Then in this case, 3 positive charge is neutralized by 3 chloride ion. Okay, 3 chloride ion. Then it will form CONH3 whole 6 in a square bracket, outside 3 plus, and then 3 Cl 1 minus, Cl minus can neutralize. Then this actually formed 1:3 electrolyte, because here also cation and anion is there. Then CONH3 whole 6 in a square bracket, outside 3 plus, now 3 Cl minus came, and compound is formed. Only cation which is inside the bracket, that is called complex ion. Here it is the cation. Complex may be cation also, anion also, both is possible. But here if positive charge is there, in the bracket, square bracket, then it is a cation. If negative charge is there outside the bracket, then it will be anion. Then here I am talking about the cation, positive charge 3 plus was there. Then that is called either cation or anion in a square bracket, that is called complex ion. But if charge is neutralized, positive charge is neutralized with anion from the outside, then it is called compound. When charge is neutralized, it is called compound, complex compound, because complex ion is there. Hence after neutralizing that positive charge, that will called compound, complex compound. If it was negative, then positive will come from the outside, just like ordinary ordinary molecule, just to neutralize the charge. Okay. Then complex cation is also possible, complex anion is also possible. Then here its color is yellow. This compound CONH3 whole 6 outside 3 plus, and to neutralize 3 plus 3 negative charge came chloride ion. Then this complex compound, its color is yellow, and you should understand here that color is always due to the cation, okay, or complex ion, whatever is that, color is due to that ion. Then its color is yellow, and here CONH3 whole 6, and it is in bracket, square bracket, outside 3 plus, then this is considered as one molecule. Okay, inside CONH3 whole 6 is there. Despite that, it is called one molecule, and outside 3Cl is there, 3Cl minus. Then ratio is 1:3 electrolyte. This is also compound is electrolyte, 1:3. 1 complex ion and 3 chloride ion. Now another example, what I have given earlier, same things. Now see cobalt. With cobalt, 1 chloride ion is attached and 5 ammonia is attached, total 6. And now outside the square 2 plus is there. 2 plus. Hence to neutralize 2 plus, 2 chloride ion will come. Then now it is became 1:2 ratio, 1:2 electrolyte, and its color is purple. This compound color is purple. Now you can ask the question, why this time 2 plus? Cobalt has now in this situation has 2 plus. Why? Then now you can understand. Compound is cobalt, 1 chloride and NH3 whole 5. 5 NH3. In the beginning 6 molecule NH3 was there. Now 5 NH3 is attached. 6 one is chloride, and chloride is negative. 1 negative. Chloride has 1 negative charge. Hence out of 3 positive, 1 is neutralized by Cl. Only in the complex ion within the bracket. Hence now outside charge became 2Cl, and that 2Cl is now neutralized by 2 chloride ion, and now ratio became 1:2 electrolyte, and now compound's color became purple because of now Cl ion attached. In the beginning only NH3 was there. Now Cl has come. That's why its color changed to purple. I will tell the reasoning also, why yellow or yellow, green, purple, all the things I will discuss about the color. Now understand that now color changed to the changed due to the Cl. 1 Cl attached to the cobalt. Now third compound, what I discussed same way, they have given 3 mole HCl, 2 mole HCl, 1 mole HCl, AgCl. That example I am telling you, why it has shown 3 mole AgCl, and why it has shown to given 2 mole HCl and 1 mole AgCl. That now you can understand. Then now third case, now 2 Cl is attached to the cobalt and 4 ammonia is attached, total 6. So then cobalt has 6 this vacant orbitals, then 2 orbital is occupied by Cl and 4 occupied by ammonia, total 6. Then now outside of the bracket only 1 plus is there. Then now you can understand why 1 plus. Now cobalt had 3 plus, then now 2 Cl has come. Cl has 1 negative, each Cl 1 negative. That's why out of 3 plus 2 2 plus is neutralized by 2Cl. Then now cobalt has only 1 plus. Then outside the bracket, complex has only 1 positive. Only 1 positive. And that positive is neutralized by 1 chloride ion. 1 chloride ion. And now ratio became 1:1 electrolyte. Its color is green. Then now this green color is due to the 2 chloride ion attached to the cobalt. Now next example I am telling you that again same 2 chloride attached to the cobalt and 4 ammonia attached to the cobalt, total 6. Then again same case, 1 positive charge is outside. Same reasoning. Then 1 positive charge is neutralized by 1 chloride ion outside. Then it is also 1:1 electrolyte, but now its color is violet. Same situation is as green. Green and now violet. Formula is the same. CO means cobalt Cl2 NH3 whole 4. Here also cobalt Cl2 NH3 whole 4, outside plus, but color is different. Why? Then both are, you can understand, they are just like isomer. Molecular things are, molecular formula is same. Structural formula, you will find that some change is there. Some change is there. And there, I will tell you. This also I will tell that are actually both are isomers. Both are isomers. Okay, I will discuss isomerism. That time I will tell you. Both are isomer. Then isomer, you know that chemical formula will be there, will be the same, and structure formula will be different. Then due to the different structure, they have different color. Okay. Now here this I already told you that last two compounds means green and violet, both are same formula. They have identical empirical formula. Cobalt Cl3 total outside is also chloride ion, and inside 2 chloride, outside 1 chloride, total 3. Then it is its empirical formula is cobalt Cl3 4NH3, but distinct properties. They have different properties. Such compounds are termed as isomers. I will discuss in details. Werner, scientist, chemist, Werner in 1898 propounded his theory of coordination compounds. He has given theory of coordination compounds. The main postulates I will discuss. Question is asked. Here all things what colored, all colored you keep in mind. Question is asked. Compound also, actually limited number of compounds are there. Limited number. Then directly they will ask question about the color also. White color produces, that I will tell at a proper place. But now question will be asked, what is the color of the compound? Then hardly, I think 9-10 compounds are there, not more than that. Common way I am talking about, which are asked in examination. Then that you, by practice, you can remember. In the beginning, you will think that how can I remember? But if you will read, minutely if you read and see, then easily you can understand. Okay. All color compound you remember simply. Colored compound you remember, it will help you. Then what are the postulates of theory coordination compounds? Now I am telling you. First, actually all postulates are important for examination and for your understanding purpose also, knowledge point of view also. Okay. Then first postulates is in coordination compounds, metals show two types of linkage. Means valency, two types of valencies it shows, primary and secondary. Primary valence is common in all molecules. What you have studied, read, one positive, one negative, and NaCl, KCl, Na2SO4, Na2SO4, CaCl2, Al2SO4 whole 3, aluminum sulfate, calcium chloride, all are common. There only primary valence is there. Primary valence directly they are attaching to the can say cation, direct cation and anion. But here in this compound there will be secondary valency also, and secondary valency is due to the central metal ion. Okay, and for that this vacant d orbital is responsible for secondary valency, remember. Then in coordination compound, metals show two types of linkage or valencies, that is the primary or secondary. Second postulates, the primary valencies are normally ionizable. The primary valencies are normally ionizable and are satisfied by negative ions. That is the common way. Primary valencies are normally ionizable, not the molecules. Complex ion will not ionize in the bracket, square bracket, that will not ionize. Outside ions are there, that will ionize. Okay, means primary valencies are normally ionizable, not the secondary. Third postulates I am telling you. Third postulates, the secondary valencies are non-ionizable. This you remember as a third postulate. The secondary valencies are non-ionizable. These are satisfied by neutral molecules or negative ions, because neutral molecules they can have lone pair of electrons, or negative ions also. Negative means they have electron, they can have a pair of electron. That's why secondary valencies are you can say secondary valencies are non-ionizable, and these secondary valencies are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number and is fixed for a metal. What is actually coordination number? Then these neutral molecules or ions which will donate electron to the d orbitals, then they will make the bond. Then coordinate bond it will make. Then that how many bonds they are making, that is called actually coordination number. Then coordination number you can tell, that is a number of ligands attached to the central metal ion. Okay, then that number is called number of ligands attached to the central metal ion, central metal atom, or central metal you can tell, central metal ion or central atom. That is that number of ligand is called coordination number. Question is asked, and for a metal it is a fixed. For any metal, as for example in this case with cobalt 6 I told you, like that way. For other metal maybe 4, maybe 5, it is fixed. Now fourth postulates I am telling you now. The ions groups bound by secondary linkage to the metal have characteristics spatial arrangement. Spatial arrangement means arrangement in a space. Okay, suppose in air you are considering some metal, and surrounding this metal ligands are attached. In a space arrangement, molecules are attached. Think like that. Imagine that metal is in the space and air, or in a space we can tell, and these are ligands are just arranged around the metal in a space. That is called spatial arrangement. Okay, there, due to this I can say arrangement, sometimes they will change the color also. Okay, due to this position change, due to the structural change, color also change. Remember it. That's why the same thing was there. 6 ligands were there, Cl2 and NH3. Cl2 or Cl2 we are same, NH4, NH3, NH3, their number was same. In two compound, COCl2, NH3 whole 4. For the two compound it was the same, but color was different due to the spatial arrangement of ligands around the central metal atom or ion. Then this I have told you about the these things. Fourth postulates: the ions or groups bound to the secondary linkage to the metal have characteristic spatial arrangement corresponding to different coordination number. Okay, corresponding to different coordination number. For this, for other metals coordination number may vary, but whatever be that arrangement will be there. In a space ligands will be arranged. Okay, in any molecules complex compound, so that this around the central metal ligands will be arranged up, down, left, right, like that. Actually, if you will see the structure of any particularly complex compound, I am telling you, then you will understand very clearly by microscope. You can see all the things. Okay, by microscope. Sometimes electron microscope, you want to see the electron also, then electron microscope you can use, but it is not found everywhere. Microscope is also not very useful, but anyhow something is better than nothing. You can see, actually a microscope will show big molecules, but electron will show up to the electron level, hence very clearly you can see there. Then you will find how in a complex compound molecules are arranged. In the middle, central metal ion will be there, and surrounding that other ligands will be there with making bond with central metal. You can see, and again you will find out of this one, you are writing in a square bracket, but in real practice there will be bracket. Only you will find that with central metal 6 points you will find same type of points are there. In the middle different type of points will be there, and 6 NH3 suppose it is attached, then 6 same type of point you will find. And again outside you will see, suppose 3 plus was there, then again you will find 3 other type of points are there. Other symbol type you can see there. This is the exact picture I am telling you. It will look like that. No bracket and this that. First central metal ion it will show by some special symbol, and 6 NH3 again same type of symbol will be there, and again far from the NH3 again 3 positive is going to be neutralized by 3 negative, then you will find 3 Cl in different symbol it will be there. Then charge also it will not show. Positive, negative, it is not written. We are telling here, this is a positive, this is a negative. Here positive, negative means that opposite character. opposite character. Correct? There nothing is written in the compound. If you see the molecules, you can't see that written positive or negative, nothing. Just opposite character. Opposite character means both can attract to each other. Same character repulsion, opposite character attraction. Okay, this you can think in this way. All chemistry will feel very easy. What I told you now, if you will think like that, full chemistry, organic, inorganic, physical, whatever you study, even any medicine, all things will be very clear. Okay? You have to just imagine this type of concept. Then you can understand chemistry will be fun for you. Okay, because on the book you can't, it is very difficult to make that diagram, 3-dimensional diagram. It is very difficult to make on the book, on the paper. Okay? Can't make diagram on the paper. Very difficult. Even in the X, Y, Z axis, it is becoming very difficult. Then I told you, you can imagine like that. Then I discussed postulates of Werner's theory. Question is asked. In modern formulation, such spatial arrangement are called coordination polyhedra. You remember this question is asked, what is the polyhedra? Then now we understood that inside the bracket, on paper you are writing that inside the square bracket it will be complex ion. But now in modern formulation, that spatial arrangements are called coordination polyhedra. Coordination polyhedra inside the square bracket. Okay, how they are arranged. Spatial arrangement is called coordination polyhedra. The spaces within the square bracket are coordination entities or complex. What is the coordination entities? Then that complex which you are writing inside the square bracket means Cl2 NH3 whole 4. Like that you are writing in a square bracket. That is actually called inside the bracket, square bracket, that is called coordination entities, or you can tell complexes and the ions outside the square you are writing Cl, 3Cl, 2Cl, sometimes SO4 also you can write, Br also you can write, whatever be. Then outside, the ions outside the square bracket are called counter ions because it is neutralizing. That's why it is called counter ions. Werner further postulated that main postulates I told you, but further I am telling you what he just postulated. Werner further postulated that octahedral, tetrahedral and square planar geometrical shapes are more common in coordination compounds of the transition metals. This again important point I am telling you. According to the Werner, that there will be octahedral first, tetrahedral second, square planar third. These are the shape called geometrical shapes and these are common. These shapes are these three type of shapes that is called geometrical shapes are more common in coordination compounds. Other are also there, okay, but these three are common in coordination compounds: octahedral, tetrahedral, square planar. Then octahedral means 6 ligands will be there, 6 octahedral. Total number of molecules will be, total number you can say ligands here it will be 6. In tetrahedral including central it will be 5. Okay. This tetrahedral 5, and in a square planar that will be 4 plus 1. It is also 5, but these 4 ligands will be in the form of a square. Okay. Then tetrahedral, they differ only in angle, tetrahedral and a square. Now, this example I am telling you, CONH3 whole 6. And here cobalt metal 6 ammonia is attached. Cobalt NH3 whole 6. Cobalt NH3 whole 6 outside 3 plus. Within the square, cobalt NH3 6 are there. And another example, here 6 NH3 are there. Then first I will tell the name, then you can understand other easily. First let me tell name. Cobalt NH3 whole 6 3 plus. First example, molecules is ligand. How many are there? Second example, cobalt Cl NH3 whole 5. Outside 2 plus. What I have told you, examples, same examples. Now, third example, cobalt Cl2 NH3 whole 4. Means 1 chloride is increasing. In the beginning, no chloride, other 1 chloride, other second chloride. And NH3 1 decreased. Then 3 I have told you. Then in these 3, what you are observing, total is 6. In the beginning, cobalt NH3 whole 6. Okay. In second case, cobalt 1 Cl and 5 NH3. Then now total 6. And in third case, cobalt 2 Cl means Cl2 NH3 4. Total 6. Then these are the example of octahedral entities or octahedral complex. Now, another example is here. Nickel tetracarbonyl. Nickel tetracarbonyl NiCO whole 4. CO means here carbon monoxide, carbonyl, also called carbonyl, carbon monoxide. Then NiCO whole 4. It is in bracket. And other is PtCl4 in bracket outside 2 minus. But in nickel, NiCO whole 4 in bracket outside no sign is there. 0, nothing, no positive, no negative. Actually, this is the CO is the neutral ligand. Neutral ligand. Okay, it has no charge. And nickel is, here it is showing 0 oxidation state. Nickel is in the metal form. Then NiCO whole 4. And another example I told you, PtCl4, it is in bracket outside 2 minus. Then first one, nickel NiCO whole 4. This is the example of tetrahedral. And these are the example of tetrahedral and square planar. Second example is PtCl4 2 minus. This is the example of square planar respectively. Because PtCl4 is in one plane. On paper you can write, arrange. Okay. Then this is in one plane. That's why it is in a square form. That's why it is called a square planar. Then this I have given example of tetrahedral and square planar. Then tetrahedral example is NiCO whole 4, total 5. 4 CO, 1 nickel. Then ligand is important here. Then this is the tetrahedral. PtCl4 here, again here is a 5. Total 5. But now it is in a square form and in one plane. That's why it is called a square planar. Then this I have discussed about the postulates. Now I want to tell about the difference between a double salt and a complex. Question is asked. What are the difference between a double salt and a complex? Now I am telling, both double salts as well as complexes are formed by the combination of two or more stable compounds in a stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, what is the formula? KCl, MgCl2, 6H2O. Then here you can see KCl is one type of salt, MgCl2 is another type of salt, potassium chloride, magnesium chloride, 6H2O. Then this is one molecule carnallite. Together it is called carnallite. But here two type of salts are attached. If it will dissolve in water, then KCl will be separated, MgCl2 will be separated. Then this is the example of double salt. Another example of double salt, then Morse salt, MOHRS. It is the name of scientist, Morse salt. Then what is the formula, chemical formula? Then actually this question is just remember, FeSO4, ammonium sulfate, 6H2O. Here also two types of salts are attached together. FeSO4 first, second is ammonium sulfate, NH4 whole 2 SO4. SO4 has two negative. That's why one ammonia is positive, one positive. Then two ammonia. Then FeSO4, NH4 whole 2 SO4, 6H2O. This is again example of double salt, because in water again it will dissolve. One part will be FeSO4, other part will be NH4 whole 2 SO4, means ammonium sulfate. Now third example I am telling you, KAlSO4 whole 2 12H2O. This is the example of potash Lm. But here is just like empirical formula only. K means potassium, AlSO4 whole 2 12H2O. But what is exact formula I am telling you? K2SO4 Al2SO4 whole 3 24H2O. This is the exact formula. K2SO4 Al2SO4 whole 3 Al2SO4 whole 3 24H2O. Okay, that is the empirical formula. Shortcut, it is the KAlSO4 whole 2 12H2O. Okay, then this is again example of double salt. This is called potash Lm. Potash Lm, actually this is common in house also. During shaving it is used. It is just like a white type of stone, like that you can tell. Not a stone. A stone also you can tell it is hard, very hard. Just you shaving time, it is antiseptic. Shaving time, just you can rub on your cheek when it is any cut and these are there. And shaving time actually it is used. It is antiseptic. Okay, this is in general used, potash Lm. That is called popularly known as Lm. But as a chemist you should know potash Lm. Okay, then these are the example of double salt, because two salts are attached. And what will happen? These salts dissociate into simple ions. These salts dissociate into simple ions completely when dissolved in water. First example I am telling you, that KCl, MgCl2, 6H2O. Then here it is two salt. KCl is 1, MgCl2 2. But if you dissolve in water, then KCl will further dissociate K and Cl, K plus Cl minus. MgCl2 also it will dissociate Mg2 plus 2Cl minus, means completely it will dissociate. Ions will dissociate into simple ions. Ferrous sulfate also, ammonium sulfate, they will dissociate into simple ions. Potassium Lm also. and potassium sulfate, aluminum ion, all it will give simple ions. However, complex ion, now I have discussed already, complex ion such as FeCN whole 6 in bracket, square bracket, outside 4 minus of this complex ion such as FeCN whole 6 in bracket outside 4 minus of K4FeCN whole 6 do not dissociate into ferrous and cyanide ions. Here understand, it's very meaningful things I am telling you. FeCN whole 6 outside 4 minus is there. Then this is the anion. It is a complex anion, example of complex anion. Already told whatever I discussed now all were cation, complex cation. Now complex anion example is FeCN whole 6 outside 4 minus. This is the anion form. Here 6 cyanide is attached to the central metal is ferrous here, iron. Outside 4 minus is there. Then now we will ask why outside 4 minus. Then now you can understand very easily. Actually, this cyanide has one negative charge. Cyanide is one negative charge. Then 6 cyanide means 6 negative charge. 6 negative charges there with Fe. If you are not knowing the oxidation state of ferrous, then I am telling you the way how can you determine the oxidation state of ferrous. Then this is the minus 6, but outside it is showing 4 minus. Then now what is the oxidation state of ferrous? You can understand very easily. Fe plus, this is the minus 6, then Fe minus 6 is equal to minus 4. Then what is the Fe value? Then minus 6 will go to the right side. It will come plus 6 minus 4. That is the plus 2. Plus 2 means ferrous oxidation state is plus 2. This I told the method to find out. The question is asked in particularly in advanced, this IIT advanced or medical also, this question is asked to calculate the distance oxidation state. Because ferrous may be in plus 2 also, plus 3 also. Then by seeing the outside value we can understand. Then here you understood FeCN whole 6 outside 4 minus. Then what is the value of oxidation state of Fe? Then Fe minus 6 plus minus and Fe plus and minus 6 is for cyanide. Then total minus 6. Fe minus 6, that is outside is equal to 4 minus. Then now Fe is equal to plus 6 minus 4, that is a plus 2. Then now you can understand why outside it is a 4 minus. Because cyanide is 6, then minus 6 and Fe is plus 2. That's why outside is minus 4. Very important concept I have told you. Then actually it is an anion. Then how will you become neutral? You have to make it neutral. Then 4 minus is there. Then 4 positive charge should come. 4 positive charge should come. Then always cation is written first. You all don't forget. Always cation is written first. Then here to neutralize this complex anion, positive ion should come. That means cation should come and it should be written first. Then K4, 4K may come. 4K means 4 positive charge, then K4, and again you write same things. FeCN whole 6, 4 minus. Now both charge are neutralized. Then in this compound K4 FeCN whole 6, this became compound, coordination compound. Now no charge is there. Potassium you can say ferrous hexacyanide or ferrous hexacyanide, you can tell. Potassium ferrous hexacyanide. Then in this, if K4 FeCN whole 6 If it will dissolve in water, then it will dissociate into ferrous 2 plus. Okay, it will dissociate into potassium and complex ion. It will give only 2 type of ions, potassium ions and complex ion. It will not give cyanide ion. This is the characteristics of complex ion. It will not give. If you dissolve this potassium ferrous hexacyanide complex, then you will get only 2 type of ions: potassium ion, 4 ion potassium, and 1 ion of ferrous hexacyanide, FeCnO6. You will get that. You will not get cyanide ion. It will be in the form of complex ion only. This is the characteristics of complex ion. It will not break into the ions. Complex ion will not break into the ions. Okay, only primary valence that will break, not the secondary. Then this I have discussed. Today I have given so much background for coordination compound, and next class I will continue. Now I am stopping only here. Thank you.